Welcome to our fourth video over the 3B13 test. And our fourth video will pick up with page number 4 on the test. Page number 4. Hopefully we have an opportunity to break the record for the most help videos on any one assignment. Will it happen? It's hard to say. We'll know soon. Page number 4 begins with question number 26. Which of the following statements is false? Letter A here is just kind of trivia in a way. Answer A here says that the letter A is used to abbreviate mass number. Letter Z is used to abbreviate atomic number. That is a true statement, although it's really not all that significant. Remember, when we write in nuclear symbol format, the mass number goes up here. The atomic number goes down here. So I always remember, if we were reading top to bottom, if we had the alphabet top to bottom, we would be reading from A down to Z if the alphabet was going top to bottom. So that's how I remember which one's A and which one's Z. But that's really kind of an insignificant question. Isotopes and nuclides have same atomic numbers. Absolutely. Isotopes and nuclides are different atoms of the same element. So if I have two atoms and they're exactly the same, they are nuclides. If I have two atoms that are twins but not identical, they are isotopes. But for them to be an isotope or a nuclide, they have to be the same element, which means they have to have atoms of the same element, which means they have to have same atomic numbers. Letter C. Letter C is a very good question. Answer C is a very important thing. Isotopes are characterized by being unstable nuclei, meaning that is a nucleus that would fall apart easily because it doesn't have the right ratios of protons and neutrons. Well, it is true that some isotopes are unstable. In other words, some isotopes are radioactive. Keep in mind that isotopes do not have to be unstable at all. In fact, for an isotope to stay around as the same atom, it has to be somewhat stable, or it would change into another atom in an effort to become stable. It would lose protons, chunks of the nucleus might fall apart. So isotopes certainly can be stable. For something to be an isotope, the only thing we need to have is same atomic number, different mass number as another atom. All right, let's move on and take a look at answer letter D. Hydrogen 1, hydrogen 2, hydrogen 3 all have one proton. That is true. In order for an atom to be hydrogen, in order for it to qualify as hydrogen, it has to have one proton in the nucleus. Or you can't even use the word hydrogen. 3 naturally occurring isotopes of carbon are 12, 13, and 14. Yes, they are. 12 and 13 are more abundant. 14 is only trace, available in trace amounts, if you remember back to our lab. All right, number 27 is dealing with the diagram above, where we have 2 electrons on the first level. That's all the first level holds, if you remember, because that first energy level is close to the nucleus. It doesn't have as much space. The second level is a little further from the nucleus. It now has more space. The second level can hold up to 8 electrons. Remember, the goal of atoms, when they chemically react, is to be left with the level having 8 or 2 in it, being left with levels that have 8 or, in the case of this inner level, 2. So they want to know which statement's false here. Statement number 1, the atom is lithium, and it could be represented by the hyphen notation lithium 7. Remember, we need to first identify, is this lithium? The red particles are intended to be the protons. There's 1, 2, 3 protons. We look at the periodic table, and we see here the element that has 3 protons in its nucleus is lithium, so it is indeed lithium. What does hyphen notation give us? It does not give us protons, it gives us the mass number. Remember, when you're using hyphen notation, they're assuming that you have a periodic table to look up the atomic number. So what are they telling us here with the lithium 7? They're telling us that this particular atom of lithium should have 7 particles in the nucleus. We count 3 protons, 4 neutrons, that is 7 particles. That is the hyphen notation. The atom above would be neutral. Neutral, it has to have the same number of electrons orbiting the nucleus as there are protons in the nucleus. There are 3 electrons orbiting, 2 in the first level, 1 in the second level, and there are 3 protons in the nucleus. This atom is neutral. Letter C. Letter C. The atom, it would become chemically, it should say stable. The atom would become chemically stable when acquiring a 1 plus charge. Well, let's find out. If it became a 1 plus charge, plus means it lost electrons. When there's a plus sign, remember, plus, lost. The T in lost looks like a plus sign as well. In other words, there should now be 1 more positive particle than there are electrons orbiting it. So if there's 3 positive particles and it's plus 1, then we should only have 2 negative particles. So if it's plus 1, it's going to lose that electron right there on that outer level. They lose them on the outer level first. So it's going to lose that electron first, and then it would be left with 2 in that inner level. 2 in that inner level would be chemically stable. Octet duet rule. If we look at the periodic table, here's lithium. It starts with 3 protons, so it starts with 3 electrons. If it's plus 1, that means there's now 3 protons and 2 electrons. There's 1 more positive than negative. If it lost 1, it would have the same number of electrons as helium. Helium, we know, has satisfied the duet rule. It has its inner level full with 2 electrons in it. We can also look over here. When we look on this periodic table, here's lithium right here. Lithium does become plus 1. Why does it become plus 1? And that Roman numeral there is also a trick for remembering it's plus 1, because they only have 1 electron. If they lose that electron, they would be left stable. Lithium would be left stable. All right. The mass number is 7. Absolutely. The mass number is 7. Mass number is number of particles in the nucleus. The same way there's a 7 here. The mass number is 7. The atomic number would be 3. Atomic number is the number of protons in the nucleus. That's true. The next one, the nuclear symbol. Remember, the nuclear symbol puts the mass number on as a superscript and the atomic number as a subscript. They do not put the number of neutrons there. 1, 2, 3, 4. Yes, there are 4 neutrons. There are 4 gray particles in the nucleus. But they add those to the atomic number, and they write the mass number in the upper left. That should be a 7 there. 7 minus 3. They put it that way because you can easily subtract the mass number from the atomic number to get the number of, or subtract the atomic number from the mass number to get the number of neutrons. Letter A, B. That should be a 7 up there. Number 28. In each of these 2 rows of elements, there's 1 that has not satisfied the octet rule. How can we tell which ones have satisfied the octet rule? Let's just kind of go through. Aluminum's 3 plus. If you look on the periodic table of elements, aluminum's 3 plus. If it lost 3, 13 minus 3 electrons would leave it with 10. It would be just like neon. It would be just like neon. That little trick for finding out if you subtract the electrons from the positive for the positive ions, or you add electrons to the negative ions and you end up with the number that's in the noble gas family, that trick works for a lot of them. We'll show you that there's another trick that we need for some of them. It doesn't always work. But let's take a look at the next one. Is krypton satisfy the octet duet rule? Krypton's a noble gas right over here, number 36. The noble gases are noble. They don't react. They're inert. Noble means that they don't react with any of the other common elements. But the noble gases don't react because they are already chemically stable. They've satisfied the octet duet rule. I minus. Minus is a negative. Negative has an N. Gain ends in an N. Negative means they've gained electrons. We now have more electrons than protons if it's negative. So if we know the atomic number, we have to add the negative to it to see how many extra electrons it has. So we come over here to iodine. Iodine's 53. 53 protons. If it's negative, it has one more. If it's -1, it has one more electron than protons. 53 plus 1 is 54. It would become like xenon. Now remember, when we say plus 1, 53 plus 1, we're adding a negative electron. That plus means you're adding a negative electron. When we subtract from it, it means you're subtracting an electron, which happens to be negative. All right. Oh, 2 minus. That 2 minus means it's gained 2 electrons. It now has 2 more negatives than it does positives. So let's go look at oxygen. Oxygen's number 8. If it's 2 minus, it's gained 2 negatives. 8 plus 2 negatives gives it 10 total. Same as neon. Chemically stable. Chemically stable. Another little trick to looking at these, for like oxygen. Here it does show you that it wants to be 2 minus. Why does it want to be 2 minus? Because oxygen is in Roman 6. If we add 2 electrons to Roman 6, we get Roman 8. So the pink one's up here. 5. If it has 5, Roman 5, we need to add 3 to get 8. If it has Roman 6, we need to add 2 to get 8. If it has Roman 1, we need to add 1 to get 8. The green ones, we would have to remove electrons to go the other way. So on these, we're taking electrons away. So Roman 1, we would have to take electrons away to get back over to 8. Roman 2, 2 electrons to get over to 8. 3, we would have to lose 1, 2. Now we're back over to 8. So we're moving that way. Just kind of how many do we have to remove to get back to here is what we're looking at. All right, let's continue down that row. What about lead 2 plus? What about lead 2 plus? Does it satisfy the octet rule? Well, now we need that little trick we just talked about. Here's lead. Right down here. Lead can become 2 plus or 4 plus. But if it's become 2 plus, has it satisfied the octet rule? Well, we come up here. It's Roman 4. It would have to lose 1, 2, 3, 4 to get back to 8. Not 2. So lead has not officially satisfied the octet or duet rule. Letter E from row 1. Which one of these in this row has now satisfied the octet rule? Let's start with arsenic, As. It's 3 minus. Arsenic right here. 3 minus means it's gained 3 negatives. It now has 3 more negatives than positives. So it has 33 positives. If it's gained 3 more negatives than positives, it would have 1, 2, 36. 1, 2, 3 would give it 36. Just like krypton, that would satisfy the octet rule. Arsenic would satisfy the octet rule. Looking on this table, arsenic for sure wants to become the arsenide ion. Remember, when it gains electrons, we change it to "ide." It wants to become the arsenide ion because 5, 6, 7, 8. If it gains 3, it goes from 5 up to 8. The pink ones are going to the right. Gain. The green ones need to go to the left, as it says up here. They need to go to the left in order to be left with 8. All right, that takes care of arsenic. What about sodium? Does it want to be plus 1? Here's sodium right here. It starts with 11 protons. It starts with 11 electrons. But if it's plus, it means there's one more proton than electron. So we'd have to have 11 positives and 10 negatives. 11 positives would mean, and 10 negatives would mean that there's one more positive than negative. So it's lost one of its original negatives. 11 minus 1 leaves it with 10, just like neon, which would be a stable outer octet. We see right over here on this table, sodium wants to become plus 1. Why? It's in Roman 1. If it's plus 1, we're moving to the left. We're moving to the left, so we would go from 1. If you move to the left, it takes you back over to the 8. It would be stable. 8 is octet. It would become stable. What about selenium 2 minus? Selenium 2 minus would also take care of it. Selenium 2 minus, 1, 2. That would do it. It would end up with 36. What about antimony? Well, helium we know is a noble gas. It's going to be stable. But what about antimony? Antimony, if we look on this table right here, Antimony's right here. If it's 3 plus, it's not going to get all the way back over. It needs to be 5 plus to